Okay, these notes are for pre-calculus, third hour on Friday, 4/12. And this is after you finish 7/5. This is the beginning of 7/6 on linear programming. So I'm not sure how far you'll get into this, but I'll just record a chunk of stuff, and then you'll just have to let me know on Monday how far you got. So linear programming is this next section. We're going to solve linear programming problems, use linear programming to model and solve real-life problems. And again, the files are big, so I will probably have to put them in chunks on my Yola site for this section. This is linear programming, a graphical approach. And when we're looking at linear programming, we're usually trying to optimize something. So we either want to find a minimum or a maximum. And often by using various constraints, we can arrive at what is the optimal either minimum or maximum value. And we usually have feasible solutions that we get, and you can kind of see this little picture down here. All the feasible solutions are maybe in this little region. Truly the most interesting feasible solutions are where these boundaries intersect, and so those would be maybe, you know, graphs of linear inequalities and then shading above or below, so we get this feasible solution. And then we're going to kind of look at what is happening at each of those points. So the objective function gives us something that either needs to be maximized or minimized. You know, we might want to maximize our profits. We might want to minimize the weight of something if it's important not to use a lot of weight as we go through. We might want to look at maximizing and minimizing various things. So when we have an objective function, and we will have objective functions as we go through this, that is something that we're just putting coordinates that are x, y values, usually from those outer edges of our shaded region, and we either want the z value that is biggest or the z value that is smallest. And a and b would be constant numbers as we go through. So because everything in the shaded region satisfies the constraint, we want to look for the optimal solution, and that's usually going to be at one of, or that must be at one of the vertices as we look at that. So this is the optimal, and I'm going to go to this next slide. This is the optimal way to find the optimal solutions. Well, I didn't say that very well. So I did add an A step. So the first thing you have to do is decide on an objective function and inequalities to match your constraints. And once you do that, then you're going to solve the linear programming problem in this way. You're going to sketch the region that corresponds to the system of constraints. The points inside or on the boundary region are the feasible solutions. Then you're going to find the vertices of the region, and then you're going to test the objective function at each of the vertices and select the value that optimize the objective function. Sometimes you want that to be a maximum, sometimes you want it to be a minimum. For the bounded region, both a minimum and maximum value will exist. For an unbounded regional, if an optimal solution exists, then it will occur at a vertex. Think about it. A region that is not bounded and maybe goes to infinity, if we want to maximize something, you know, we'll just never get to the maximum value. So here's our first problem, and I am going to pause this a moment because because I see that my picture is a little hard to see on this slide. So Okay, I kind of cleaned up my slides a little bit, and now we'll move on this one. So it says find the maximum value of z equals 3x plus 2y, which is the objective function, subject to the following constraints. X is greater than or equal to 0, y is greater than or equal to 0, x plus 2y is less than or equal to 4, and x minus y is less than or equal to 1. So in this situation, we don't have a problem attached to it. We're just going to do the mathematics as we go. And I will ask that you're graphing this, and I'll look at that when I get back as we go through things. So I will color code these. So first, I'm just going to graph x is greater than or equal to 0, and I will use a solid line here and kind of a green color just to be able to do these. And oh, something didn't go well there. And let me try that one more time. And then um, there we go. X is equal to 0 is just this vertical line right here. And so x is greater than 0 would just be kind of, oh, that is not me scribbling with that, would just be everything over this way. And then for the next one, y is greater than or equal to 0. Again, y is greater than or equal to 0. Please use a straight edge when you're doing this so that things are easy for you to see. Y is equal to 0 is this line right here, and then y is greater than 0 is everything up here. So we can see that we're in like that first quadrant with just those two constraints that we have. And then we'll look at the constraint of x plus 2y is less than or equal to 4. And I'll just do my work over here and then I'll go back to that. So x plus 2y is, less than or equal to 4. And so we're going to graph x plus 2y equals 4, and we're going to use a solid line. When we get y alone, 2y equals negative x plus 4. Y equals negative 1/2 x plus 2. And so we have a y-intercept of 2 and a slope of negative 1. So I'll just plot some things here. Y-intercept of 2. A little hard to see, but I think it's right there. And then a slope of negative 1/2. So down 1 over 2, down 1 over 2, down 1 over 2, down 1 over 2, and down 1 over 2. So I get some good points that I can kind of match. And that should be this line right here. And then I need to check a point to see if it'll work. I can check my favorite point, 0, 0, because the line doesn't cross through that. So I'll check 0, 0 in that inequality. So 0 plus 2 times 0 should be less than or equal to 4. 0 is less than or equal to 4, which it is. And so that means my shading for this line will be below here as we look at that. And then as I go through this a little bit more, then I get this next equation, which is x minus y. Ooh, I'll write that a little better. X minus y is less than or equal to 1. And so x minus y is equal to 1. Negative y is negative x plus 1. Y is x minus 1. So that's a y-intercept of negative 1 and a slope of positive 1. And I have to say I'm having a little trouble seeing my graph, so I'm actually going to bring my grid to the front a minute. Order bring to the front, and just so I can see my grid points a little bit better. And so my y-intercept is -1, my slope is +1. And so -1, and then up 1 over 1, up 1 over 1, 1 over 1. And I like to put a lot of points because when I drew that straight line drawer, sometimes it's a little hard for me to exactly see where I need to go. And so there's my line for that. I'll extend that out a little bit. Oops. As we go, I can again check my kind of favorite point, which is 0, 0. And when I check that this time, 0 minus 0 is less than or equal to 1. I'll check 0, 0. Let me slide that up a little bit. And 0 is less than or equal to 1. And that is true. So I kind of get this as my shaded area. So then if I look very carefully here, it's a little hard to see, but I get this region, and I'm gonna just I'm gonna clone this page. And if you remember, I can't have all of this on here anyway. So I'm gonna erase off all of my shading at the moment. And I know that where this shading is going to be is kind of down in this little region that is kind of right here. And I'm just going to have that little region shaded on my graph, and that way my file's just a little smaller. And then I'm going to find those edge points. So the point right there is 0, 0. The point right here is 1, 0. This point is 2, 1. And this point up here is 0, 2. So those are my points that I can look at to decide where my maximum value is as I go. And now I'm going to look at my objective function and kind of see where my maximum value turns out to be. So I think I'm going to slide that just to there, and I'm going to look at that z, and I'm going to just maybe block some of this off and make it a little white. Oh, just kidding. And let me try that one more time and make sure I have a bunch of white stuff here. So I'm just blocking off some of that graph paper so that it's easier to see. So my objective function is z equals 3x plus 2y. And I can't see it right now, but there we go. I want to find a maximum value, so I want the biggest z value I get when I use those green points that I have kind of marked off there. And I'm just going to try all of them. So I'm going to try 0, 0, 0, 2, 2, 1, and 1, 0. And I'll just put those in the objective function and see what I get. So z equals 3 times 0 plus 2 times 0. So that's 0, obviously not a very big answer. Z equals 3 times 0 plus 2 times 2, which is 4. Z equals 3 times 2 plus 2 times 1, which is 6 plus 2, so that's 8, has potential. Z equals 3 times 1 plus 2 times 0, which is 3. And so the optimal solution happens when x equals 2 and y equals 1. And so we want to be able to state that as well. And so let me just find a little more space here. And I'm going to say the maximum, let me try that again. The maximum value is 8, which is that answer right there, and it occurs, at 2, 1. And so we have optimized that, finding a maximum. You know, not super interesting, but if we needed to, if we really wanted a minimum with that objective function, then it would have happened at 0, 0, just to kind of let you know. And sometimes if I can't save my files, you'll see in a couple slides, I think I have like the answer printed from the book authors. And so here's those 4 vertices and that maximum value. And then, you know, we can try other points in the interior. Just notice that there's some examples. Notice none of them are as big as the 8 that we had as we went through that. And then to to think about why that maximum has to occur at a vertex, think about writing this objective function in slope-intercept form. So if you look at my kind of writing there, maybe I'll just rewrite that. So z equals 3x plus 2y, and so then negative 3x plus z equals 2y, and then negative 3 halves x plus 1 half z equals y. So that's how they're getting that equation there. And that's maybe a little clearer than this one. So they just jumped in and said that. And that's kind of a family of lines. Z over 2 is the y-intercept, and the slope is negative 3 halves. So then I have this other picture, and this is just kind of to get an overview of this. And so there's infinitely many lines that we can have that have that slope of negative 3 halves, and you can kind of see them going over and over that page, and notice that the graph passes through one or more vertices of the region as we go. And so that just kind of gives you a little overview of that. So let's do one more problem as we look at this. Minimizing an objective function. Now we want to minimize. Find the minimum value of z equals 5x plus 7y, where x is greater than 0 and y is greater than or equal to 0, and y is greater than or equal to 0. You'll notice often that whatever those variables are, x and y, a lot of times they have to be positive. You know, it's how many of something you're making, or and well, often that is how many of something that you're making. And then there are other constraints. Just a little reminder, when we get to the end of all this and you have to answer some questions, this is called the objective function. So you might be asked to tell the objective function, and then these are considered the constraints. And those x is greater than 0 and y is greater than 0 can be kind of considered some like maybe hidden constraints as we look at that. And so make sure that you know what those things are. So we're not even going to graph these x is greater than or equal to 0 and y is greater than or equal to 0. I have a little first quadrant grid here, and so we're going to just kind of know that's what we're looking at as we go. But do notice all of my lines are solid lines here as well. So we are going to kind of have that going for us. And then we're just going to take a minute and graph some of these, and I'll start with 2x plus 3y is greater than or equal to 6, and so 3y is greater than or equal to negative 2x plus 6, y is greater than or equal to negative 2/3 x plus 2. And you'll notice sometimes it'll be hard to graph this in the first quadrant. Maybe the y-intercept is not an easy to find point. And when that's the case, we can always pick an x and y value that would just make work in that and kind of see what happens. So this is x equals 2 is the intercept, and the slope is negative 2/3. So down 2 and over 3. Really, I'm only going to get 2 points on there, but that should be enough for me as I go. And oh, somehow I accidentally am grabbing that instead. And so there's my my line for my constraint, and I'll just make it a little bit longer here. And y is greater than or equal to, so we'll try our point 0, 0, and we'll check 0, 0. And when we do that, 0 is greater than or equal to 2, and 0 is not greater than or equal to 2. So this is not in my section. And I am going to use a crayon, I think, for these. And so I'm going to shade above here. And I know my x and y constraints kind of go over that way. And then I'll just use another constraint, 3x minus y is less than or equal to 15. And solid line again, negative y is less than or equal to negative 3x. Oops. Negative 3x plus 15. Don't get caught here. We're going to divide by negative 1 on both sides. So remember, with an inequality, we have to flip the inequality. Y is greater than or equal to 3x minus 15. And so now that has, you know, y-intercept of negative 15. I don't have a graph that shows that. So I'm just going to try to pick some convenient points, plot a couple points. I'm still going to use this value. Let's just let x equal 5, and I think I can get that on my graph, because if I do that, then, when I'm graphing my line, just y equals 3x minus 15, just to kind of let you know that's the line that I'm going to do. And so if I put in 5, 15 minus 15, I get y equals 0. So there's 5, 0. I'll try x equals 6. 6 times 3 is 18 minus 15, so I get a y equals 3. Just some convenient points that I can plot on here. So 1, 2, 3, 4, 5, 0. So there's a point. And then 6, 1, 2, 3. And so there's my 2 points that I'm going to have. I'll draw in this line, and then I just have to check. And when I check my point, it doesn't go through 0, 0. I'll check 0, 0. I'm going to check it in that very top one. And when I check 0, 0, I'll get 0 is less than or equal to 15, and 0 is less than 15, and so we would include that point. So I'm going to take my crayon again, and this time I'm going to put my constraint here. And since I know I have that blue line constraint, I'm not going to cross that. I know I have the y equals 0 and the x equals 0 as boundaries as well. So I'm not going to shade there. I'm just kind of zeroing in a little bit on where things are. I could have gone a little higher there. Then we'll look at another constraint. We've got negative x plus y is less than or equal to 4. And so y is less than or equal to x plus 4. Y equals x plus 4, another solid line. I've got a y-intercept of 4, 1, 2, 3, 4, and my slope is 1, so maybe I'll slide that a little bit. I can go 1, 1, 1, 1, 1, and 1. Now, notice the red line and the green line are not parallel to each other, but they aren't going to intersect on my paper. But that should be just fine. And so I'll draw that in as carefully as I can. And then I'll check my point. I can check 0, 0 again because it doesn't go through there. When I check 0, 0, I get 0 on the left. 0 is less than or equal to 4. And 0 is less than 4. So it's going to be included in that area. So here's that is going to be included. If I was going to shade everything, you know, from that line, I would shade it like that. But since I'm kind of working in this little area that I have going here, I'm just going to shade below, and I'm just going to keep it within these other constraints. So I'm kind of just getting my shading and my constraint area as I do this. And then the last one that I'll do is going to be, and I'll use maybe a purple marker for this. And my last constraint, 2x plus 5y is less than or equal to 27. 5y is less than or equal to negative 2x plus 27. Y is less than or equal to negative 2/5 x plus 27 over 5. A little hard for me to kind of plot points and kind of see what happens there. So again, I'm going to go back and just this is y equals negative 2/5 x plus 27 over 5. I'm going to put in some values and just kind of see what happens. I notice if I put in x equals 1, that I'll have negative 2/5 plus 27/5, and so that's 25/5. So that's y equals 5 there. Maybe I'll find another point as well. If I put in y equals 1, I just am looking at my problem and thinking if I go y equals 1, I'll have, well, that might be, well, I'm going to go up to the beginning equation when I do y equals 1. So 2x plus 5 times 1, which is 5, equals 27 on that boundary. When I subtract 5, 2x equals 27 minus 5, which is 22. X equals 11. That's still not going to be on my graph, so that's not going to work well. Let's pick y equals, or x equals 6. And so it's kind of down a little lower than 2 times 6 plus 5y equals 27. And then 12 plus 5y equals 27. Subtract 12, 5y equals, I'm kind of down in the corner here. Let me go up a little higher. And 27 minus 12 is 15. Y equals 3. So that gives me a better point, 6, 3. And, you know, I'm trying to stay on my picture here. So I have a point that's 1, 5. 1, 1, 2, 3, 4, 5. And look, that happens to be where something else intersects. And 6, 1, 2, 3, 4, 5, 6, 1, 2, 3. That's also another point that intersects. I'm going to use that purple color, make it a little thinner. And yeah, let me just draw that. And then I'm going to connect these. Might have to fix this one a little bit. There we go. And then I'm going to try value. I can try my 0, 0 again. And so let me use that. When I check 0, 0 in here, 0, 0, I get 0 is less than or equal to 27. And 0 is less than 27, so I'm going to go below this boundary. And then really, I know I'm going below, but I've got these other edges here as well. And so what I'm going to do is I'm just going to say, well, here is my bounded region. And maybe I'll make it darker. Oh, excuse me. I had to sneeze and it didn't go. Okay, so there's my region that I want. And so now I have to find my key points that are on there. And as I look at those, and maybe I'll write them in here in a yellow color because I'll be able to see them. That point is 0, 2. This point is 0, 4. This point right here is 1, 5. The point over here is 6, 3. This point is 5, 0. And this point is 3, 0. So that's what I'm looking at. I'm going to clone this page and then kind of clean it up a little bit. And so if you want to look back, that's all going to be on there. But I can get rid of some of this as well. And I'm going to just erase off all this because it helps my file be not as big. And that all this is on the previous slide now so that I cloned it. So I'm going to just get rid of all of that stuff. And then I'm going to reshade this as I look at it and rewrite in those points. So I'll just shade it kind of a little more lightly. There's my region. And then here are my key points again. And I'll just label them on here again. 0, 2, 0, 4, 1, 5, 6, 3, and 5, 0, and then 3, 0. And so then I'm going to go now to my objective function, and I wanted to minimize this objective function, so I'm going to use all of those points, put them in that z equals 5x plus 7, y, and kind of see what happens. So I want to be able to see all of those. So z equals 5x plus 7y. And so I'm going to put in 0, 2, 0, 4, 1, 5, 6, 3, 5, 0, and 3, 0. And I'll have you guys do that and then see what that minimum value is, and we'll look at that maybe again on Monday.